for matching problems by comparing covariates. Modern machine learning techniques are used to perform a variety of matching tasks, such as classification, in which you are trying, for example, you're trying to classify if it's a sheep or a goat based on the number of steps it took in a day. And the other task could be verification. In this case, if you're given two sets of data sets, you want to find out whether they came from the same distribution. In contemporary models, we take the data, we put it into a complex model that uses the high dimensional vector space to model some latent characteristics of the data and uses this information to make a prediction. However, an alternative strategy, and a much simpler one, could be to use readily available covariate features or easily determinable covariate features and to perform the matching. For example, in speaker verification, the covariate features could be the age of the speaker and the ethnicity of the speaker. And based on just these features, we might be able to determine if these are the same speakers or not. Before we get into what we are actually doing, we want to clarify what we are not doing. We do not propose the next best machine learning algorithm, neither do we want to beat the state of the art at some task. What we are doing actually is, given some easily determined covariate features, we want to find out how well can we do on task without performing some complex estimation of a complex function. So we formulate the problem as in Shah et al. Specifically, we assume that the true covariates are drawn from a probability distribution, in this case P sub Q and P sub G, and are passed through a noisy channel, in this case H and J, which corrupts these covariates and into the observed covariates that we see that are C tilde P and C tilde G. The noisy channels in this case could be human measurement error, or it could be an imperfect classifier. So our specific contributions here are, we look at the assumptions the Shah et al. Made, namely that there is no notion of distance between covariates. So if you have a pair of humans, then female American would be equally different from a male American and a male Indian, which is indeed not the case. The other issue is that the covariate features are assumed to be discrete, which may not hold in many of realistic scenarios. We realize these assumptions and determine the performance of the framework on classification and verification tasks. So adding a notion of distance. Basically, we consider that the classifier modifies each covariate in the covariate vector independently of each other, which means that if the noisy channel corrupted only one feature, it has a higher probability. That feature vector has a higher probability compared to another feature vector in which multiple features were corrupted. With this modification, we applied the framework to the same synthetic dataset proposed by Shah et al. And we obtained a 22% improvement in equal error rate compared to their numbers. Now, making the framework continuous. To do this, we consider that the covariate values Cp and Cg are continuous valued numbers, and the noisy channels add an additive noise with epsilon, which is sampled from a truncated normal distribution, assuming that the covariate features are initially bounded. We apply this technique to the classification task. In the classification task, we are trying to optimize the following program. Essentially, we want to select a covariate value to perform the matching such that it maximizes the probability of correctness given a particular noisy observed covariate value. And once we have this covariate value, we find an entry in the gallery set or in the set of classes that matches the selected covariate value C cell. We are currently performing experiments for this task and we will report results soon.